Hello, this is Mrs. Scarple, and I am going to take you through the retrieval and get you started on lesson 4.2 so that you can work on the practice in my absence. The first part of the retrieval, we have absolute value equations that we're going to solve. And notice it says there are two solutions. So I'm going to use example 1 to explain why there are two solutions. So I'm going to take you to a number line. And we know that with a number line, generally we have 0 in the middle, and then we have positive values going one way, and we have negative values going the other way. Now if you think about the definition of absolute value, it's the distance a number is from 0 on the number line. So the absolute value of what number is 23, or what number is 23 units away from 0 on the number line? Well, hopefully the value of 23 comes to mind. This is a distance of 23 units. But we also have one on the other side. We have negative 23 is also a distance of 23 units. So the solution for number 1 is that x equals 23 or x equals negative 23. So we need to keep that in mind, that when we're solving an absolute value equation, we can have at least, or up to, I should say, two solutions. When I look at number 2, I need to remember that w plus 8 represents one value. So what value is 15 units away from 0? Well, if we think about the previous example, we know that 15 is 15 units away, so the value of w plus 8 could be 15. But we also know that the value could be negative 15 on the other side of 0 on the number line. So we have to solve two equations. In each of these equations is going to be the same undo steps because the expression that's inside the absolute value doesn't change. So I'm going to subtract 8 on each side. And for the first equation, we're going to have w equals 7. And do the same thing with the second equation, subtract 8. Now notice, this isn't going to be negative 7. That's a common misconception about these absolute value problems. When I combine negative 15 with negative 8, that's actually negative 23. So it's not that the solutions are necessarily opposite. That only happens if our expression inside the absolute value is just the variable. But when we're doing something to the variable, we have to set up two equations that are set equal to opposite values. So our solutions here are w equals 7 or w equals 23. Now keep in mind, in both example 1 and example 2, the absolute value was isolated. There wasn't anything being subtracted from it or being multiplied with it like there is on number 3. So before we do any solving, we must isolate the absolute value. So I'm going to start with adding the 19, because that's the last thing I'm doing to this absolute value. So undo the minus 19 by adding it, and we now have 2 times the absolute value of x plus 3 equals positive 4. And you don't distribute through an absolute value. So what we need to do, this is 2 times the absolute value, we have to divide by 2. So now we have the absolute value of x plus 3 equals 2. Now I can continue solving. I know that x plus 3 represents one number that has an absolute value of 2. That one number could be positive 2, or that one number could be negative 2. So subtract 3 from each side of the equation, and we have x equals negative 1. Subtract 3 on each side of the other equation, and again you'll see it's not opposite values but actually two distinct values. We have x equals negative 5. For the next part of our retrieval, we're going to be writing equations in vertex form. Remember, vertex form is f of x equals a times x minus h squared plus k. A is the stretch. The point hk is the vertex. And if we have a negative a, that means it's going to be reflected. It's going to be turned upside down. So given this information, we're going to write a new function in vertex form, g of x, that fits the description. So f of x is originally x squared. We're going to shift it to the right 7 and down 19. What that information tells me is that my vertex, if it's to the right 7, my vertex is 7, down 19 is negative 19. I have my vertex. It does not describe any stretch. It does not mention any reflection. So this equation is going to be g of x equals x minus 7 squared. This is always the opposite of what the point is. And then it's a plus k, but our y value is actually a negative 19, so instead of writing plus negative, it's just minus 19. And we have our equation in vertex form. If we take a look at number 5, left 12, so that places my vertex at negative 12 for the x value. Reflect vertically, that means my a value is at least a negative 1, and shift up 28. So that makes the y value of the vertex 28. So our equation will be g of x equals, you can write negative 1 or you can just write negative, parentheses, x. The opposite of negative 12 is plus 12 squared, and up 28 is plus 28. And there you have your vertex form. Now the reason we had these values or these problems in our retrieval is because when we finish our work with piecewise functions, we're going to start working with absolute value functions. So it's going to be important to understand how absolute value equations work, as well as how their graphs relate to those of parabolas, because there are some similarities. For this particular lesson, our learning focus is to graph piecewise functions, interpret piecewise functions, and determine if all piecewise functions are continuous. Now, when we say continuous, there are no breaks. Everything is connected. So we're going to see if all piecewise functions are connected like we saw in lesson 4.1 as we continue through lesson 4.2. I'm only going to get a start on this lesson. I'm not going to go through the whole thing. Again, this is because I'd like you to have some time in class to practice in my absence. So we're still talking about Rashid, and he is off on another bike ride. He has a route that he likes to do on his own and has modeled his ride with the following piecewise function to represent the average number of miles he travels in minutes. So we have 4 segments of his ride with different intervals. So the function is representing miles. That means this portion of the piecewise function gives me my distance in miles. And since we're traveling in minutes, that means my domain is intervals in minutes. So we're going to keep that in mind as we go through this. So if you look at these subfunctions and you look at these intervals, what are some things that you notice? You might notice that we're using point-slope form to write our subfunctions. You might notice that our intervals have different lengths of time. You might notice that the x value that starts the interval is the x value used in our point-slope form. You might be wondering how we could find the value for a and b. You might be wondering what these slopes are going to be like. I am just going to go through number 1 and number 2. Again, just to give you a little bit of a taste of what this lesson is going to be about. When you finish this video, you will be able to at least do the problems like the retrieval and any that ask for domain or average rate of change. So the domain for this function, since we're talking about the function as a whole, for the domain of the function, you want to look at where the first interval starts and the last interval ends. That gives you your domain. So our domain, and I'm going to write this in what we call interval notation, starts at 0, and it's a square bracket because 0 is included. We have the underline on our inequality, and it goes up to 100. Again, a square bracket because the inequality is underlined. What does it represent in this context? What it represents is Rashid's bike ride lasted for 100 minutes. Because we started at time 0, we ended at time 100, and again our domain was in minutes. For number 2 is asking us to find an average rate of change during the interval 20 to 50. So if we look at the interval 20 to 50, well, we have our first interval ends at 20, so we'll use that to find the value at the end of 20 minutes, and then the 50 is the end of the interval for the second subfunction. So I'm going to find those two distances. I'm going to find g of 20, and I'm going to find g of 50. So g of 20 is 1/4 times 20 is 5, and g of 50 is 1/5 of 50 minus 20 plus 5. So 50 minus 20 is 30, so we have 1/5 of 30 plus 5. Well, 1/5 of 30 is 6 plus 5 gives me 11. So, and these are actually distances. So at the end of 20 minutes, Rashid has biked 5 miles. At the end of 50 minutes, Rashid has biked 11 miles. Now for the rate of change, we're talking miles per minute. I'm going to take and find the difference in my miles, which is 11 minus 5, and put it over the change in my time, which was 50 minus 20. And what we see is that we have 6 over 30. So you could think of this as being 6 miles in 30 minutes. You could also simplify the 6 over 30 and get 1/5 and think of it as being 1/5 of a mile per minute. And if you go back and you look at our sub-function for the interval from 20 to 50, you will see that we have that rate of change as our slope. So I believe if you're working within an interval, you can just go off of the rate of change or the slope of that sub-function. Now, if you're covering different intervals, you will have to find the different values, and you will have to do the process that I did here with the change in distance over the change in time. And this is where I will pause, and we will pick up with number 3 in class on block day.